Can you all see this, class? This is what I
Okay,
see.
now it says it's recorded. I think you're good.
All right, I don't know what I did, but I don't think I did anything. Y'all hear me though,
I
okay?
think I was doing the click recording, but I'm not sure.
Well, anyway, whatever, I'm thankful. Now follow me on this. This is the relationship, all right? What implies is if there is no change in current with respect to time, this looks like a short circuit. There's no voltage across it. Do y'all follow me? Now, listen carefully. If you're not familiar with this, it's real important you listen. With the capacitor, if nothing was changing with time, it looked like an open circuit, right? Do y'all remember that? The capacitor looked like basically an open circuit, just two dangling wires. But with the inductor, when nothing is changing with time, it looks like a short circuit. It just looks like a piece of wire, okay? Now, what an inductor does, without writing a lot of mathematical equations, is this. It resists the change of current. So if there's 6 amps flowing and that tries to change, it will create a voltage that will try to prevent that. Just keep that in mind. It resists change to the current already there. And if nothing's changing with time, it looks like a short circuit. Are you with me? One other thing I better say, because I'm getting questions left and right about this. And I'll write this out. It's not part of the policy in the statement of the course. The lowest quiz grade is dropped. Somebody, I don't know how many people asked me a variation of that. All right. The first quiz is scaled. The last quiz is going to be scaled by 3 points. Now, I got a whole bunch of questions, so I hope this answers them all. The last quiz, because I felt it was a bit too challenging, the last part will be scaled by 3 points. Do you all hear me? All right, I'll write it out later, but I'm just telling everybody. And please, if you're worried about your grade, I'll talk to you about it. But as of now, you can do math better than I can probably. You can see that we still have 40% on a final exam, 30% on a midterm. That's 70% of your grade is out there. You all follow me? So don't ask me if I'm passing or failing because there's so much left undone. You can do the calculation yourself to see what your what your quiz average is. I can't do that for you. But what I'm trying to tell you is don't panic. Just keep your head on straight and work hard. Don't get depressed. Now back to this. This is important. So now what I'm going to say, remember a capacitor looks like an open circuit when nothing changes with time. Agreed? An inductor looks like a short circuit. I'm going to start with the most basic problem first. And actually, I'm going to write the equation for the current in an inductor. Before we looked at the voltage on a capacitor. For an inductor, it will have this form for all transient solutions that we consider. We're not going to do second order transients or higher order transients. First order transients means there's a switch, it's got a DC source, and it's either turned on or off. That's all it means. Do y'all follow me? And you have a resistor and a capacitors. You have resistors and inductors, nothing more than that. I of t will be equal to some k1 e to the minus t over tau plus k2. That's the equation for the current in the inductor. The constant tau that we calculated before was L over R Thevenin, right? That R Thevenin is the Thevenin equivalent resistance across the inductor after the switch changes state. Are you with me? Everybody. Now, thumbs up on, are you hearing me? Just let me know you're hearing it. You got it. K2 is what? Anybody want to tell me what it is? You want me to tell you? Anybody?
Is the voltage as t
Not voltage, no voltage, current.
current as t goes to infinity?
Right, y'all hear that? It's the current as t goes to infinity. Very important. So K2 is I as t goes to infinity. Now, with that in mind, I'm going to go ahead and give you the most basic circuit. We're going to work a few problems, but the most basic circuit, in my opinion, at least one of them. This is it. I'm going to have a resistor R, and go ahead, make it 10 ohms for kicks. I'm going to have a voltage plus to minus 10 volts, all right? Then I'm going to have a switch. I'm going to have another resistor right here, and I'm going to have an inductor. I'm going to say the switch goes from closed to open at t equals 0. Y'all follow me? Y'all with me?
Yes.
Now what I want is just this. I want the current as a function of time for t greater than 0. So for t greater than 0, I want I of t. That's what I'm after. By the way, this is a very standard question that you'll probably see variations of on the SAT or ACT exam. You'll see it on your GREs, stuff like that. If you take a scientific GRE, it's a very basic question. All right, now, I told you before that an inductor looks like a short circuit if nothing's changing with time, right? So for t less than 0, what do I replace that inductor with, class?
Why?
Just a short circuit. I'm going to draw it because people will have questions. That's the current through the inductor for t less than 0, right? You agree with that drawing? It's a lousy drawing, but you all agree with it?
Yes.
Yes.
All right, now I have a question for you. Jessica, not you. All right, how much current flows through this 10 ohm right here? Anybody?
All of the current. 0.
0, right? None, because it's in parallel with a short circuit. Can everybody hear me on that? The short circuit will take all the current. Isn't that right, class? How many say this? I'm really trying to make sure you see this point. I assume it's obvious, but I may not. Connor, do you see it? You're giving me a hard stare. I'm just curious. Yes?
I've got it now. I just had to think about it.
Just think about it, everybody, because this is critical. I say this again. This is critical that you see this, and it becomes intuitively obvious. If you have a short circuit across a resistor, all the current goes through the short, period. No exceptions. Got that? All right. If that's the case, what is that current? Jessica, no. And the last person that answered, no. Somebody else.
The 10 over 10, I equals V over R.
1 amp, right?
Right.
Whoever said that. Y'all agree with that? Everybody. I mean, just nod your head. Do something so I know you either agree or disagree.
Yes.
Don't be afraid to disagree. All right, so that's the first part. We got the current for t less than 0. We're going to need that. Now, we need the current for t equal infinity. It goes to infinity. But what I've got to do is write the circuit, redraw the circuit. So for t greater than 0, what happens to this circuit? When that switch opens up, what effectively happens? In your own words, anybody. Not you, Jessica, and not anybody that's responded. Anybody else. When that switch opens, what effectively happens to all this? Anyone?
It all goes away.
All right, thank you, John. Y'all agree with that? It's gone forevermore. Ignore it. So when we draw this circuit, we have this. Now we have that 10 ohm that was ignored, and we have this inductor, right? This is the direction of current that I've chosen, right? That's I of t, right? That's L equal 10. I already know the current t less than or equal to 0, right? All right, what is the current I as t goes to infinity? Anyone that has not answered before? Somebody that hasn't answered before? Anyone?
There wouldn't be any current because there's,
All right, it would go to 0. Technically, the value is 0. Do you agree, John? Are you? All right, 0. All right, we got 2 of the 3, right? Now, the next thing, and I admit I made this very simple for a reason. So we all have confidence in a very simple, obvious problem. Then we can move on to more difficult problems, all right? Now, what is R Thevenin? Well,
Could you start the paper real quick?
don't answer this yet. I'm just going to make this absolutely apparent to you. For R Thevenin, you can literally imagine that inductor being torn out of the circuit and 2 dangling leads there. You follow me? What is the Thevenin equivalent resistance seen between those dangling terminals? Somebody that hasn't answered. That means no John, no Jessica, no whoever. No John. Anyone?
Would it be 10 ohms?
Sure, it's just 10 ohms. And I'm forcing you to interact here for a reason, because I think some people, but I might be wrong, are probably doing many other things concurrently. And you need to be attentive here. I mean, I have people accusing me I'm not teaching, and this is, in my mind, a bit concerning because I don't know how else to teach. All right, so it's 10 ohms, right? Now, anybody who's answered, don't answer. What's the next thing I'm going to get with that 10 ohm R Thevenin? I need one thing that's essential, comes right from that. Class, somebody else.
Tau.
Oh, yeah.
Say it though. Tau, what is tau? You're right.
Tau is L over R Thevenin.
Right, and in our case, it's 10 over 10. Nice number 1, right? Just 1 second. You agree? Whoever's that? Is that Brantley, were you answering? I don't
That
know
was
who-
me, Brooke.
Oh, Brooke,
Yes,
thank
I
you.
agree.
Are you all with me though? Everybody? Right? All right. Now you put the thing together. Now I have I of t is equal to k1 e to the minus t over 1, so I'm just t, right? Plus k2. We figured out k2 was what, class? Anyone
0.
know? 0, right? So ignore k2. I can put down a 0, but it's kind of meaningless. How do we get k1? Somebody who hasn't answered.
Could you substitute t equals 0?
Absolutely.
And
What do we, right, at t equals 0, what do we know?
I equals 0?
Yeah, and what value is that? You're right. Anybody want to help him? Go ahead.
Would that just be k1?
Well, yeah, it is K1, but what's the numerical value? I feel like a lawyer trying to pull out a term from somebody on witness. You follow me on this? What is it, class? Anyone? Help them out, anybody.
1 amp?
Yeah, it's 1 amp, right? So you put 1 is equal to K1 e to the minus 0. E to the minus 0, I say over and over again, is 1, right? Anything to the 0 power is 1. And 0 minus is 0 plus. So K1 is 1. That means, and I'll put it right here, that means for this circuit right here, I of t is just equal to e to the minus t amps. It's that easy. Do you agree with me? I'm not done yet. Now, please listen to this next part. This is where people mess up. That current is flowing in this direction down. It's going this way. It's going this way. It's going this way. Do you all agree that that is the direction of the current that I've selected, right? All right. If I was to put V of t here, what would that V of t be for t greater than 0? I want you to take a look. Notice the pluses on top, the minuses on the bottom. Anybody? Somebody that has an answer too. Not Reese, not Brooke, not Jessica, not John, not whoever. Somebody else. You're waiting me out. All right, I'll call on someone. Gabby.
Sorry, what was the question?
What is the voltage between here and here? We know the current I of t, right?
Yeah,
So I of t times R would be a voltage, but wouldn't it be this voltage? positive current in is the positive terminal on that resistor, correct?
Yeah.
So what would the voltage be when it's that polarity?
Negative.
Sure, it'd be minus R, which is 10 times I, which is 1, or minus 10 e to the minus t volts. Do you all agree with that? How many do? Now, I'm saying that for a very important reason. On the upcoming quizzes, I will ask for this type of information where polarity is a big deal. If it is positive in the right value, it is still wrong, massively wrong if you're telling somebody that voltage that has to do instrumentation on a rocket. Do y'all follow me? Polarity becomes critical in electrical and computer engineering because it can kill somebody if you don't have the right, if you don't identify it correctly. So that's the reason you have to understand how to get a positive versus a negative polarity. You understand why too? How many do here? Okay. All right. I appreciate that. Now we're going to go on to the next phase. I'm trying to do this methodically. I gave you a bunch of problems, a whole bunch of problems. Is there any problem that jumps off the page at you that you, and I gave you solutions that you would like me to explore or discuss? Any problem at all? I'll pick one if you don't have one, but I'm trying to give you as much freedom as possible. Anybody? Okay. I'm surprised, actually. I figured at least one problem. I know we won the game, but surely some of you at least took a peek at this because it's coming right at you.
Like, could you do a 3.42?
Yeah, and for everybody's sake, let me put this up here. Whoever asked that, John, was that you?
Yeah, that's me.
Thank you. All right, I'm going to put this up here. I want everybody to take a look at 3.42. Now, I know you're not electrical and computer engineers. Some of you are mechanical, some of you are industrial, some of you fiber and polymer. I don't know how many civils we have in here, if any, but we have a variation, I mean, a whole bunch of diverse backgrounds, right? Here's the problem. Now, I want you to take a look at this. The switch opens at T equals 0, right? I'm going to ask a few things. Anybody can answer. When that opens at T equals 0, is there any energy source left in the circuit for T greater than 0? Anybody can answer this.
Yes.
Think about it. When that opens up, is there any energy source? Nothing can flow, right? Right? Isn't effectively that energy source, that 6 volts, taken out of the circuit, people? Do y'all agree with that?
Yes.
If it's taken out, what do you know the current through the inductor as T equal infinity will be?
0.
How many know it's 0 just by inspection, right? Agreed with that? Just by taking one peek at this, you got that. Now, next, before I go any further, we know for T greater than 0, that switch is open, right? If that switch is open, isn't that 6 volt source effectively gone? You agree? You can ignore it. Agree? How many do? It no longer has an effect because it's only tied to that circuit by one connection, and one connection won't do it. It takes at least 2 for any current or voltage to be felt by the circuit remaining. You follow me? It takes at least 2 points of contact. Here you only have one. It's only connected here. This point is gone, so it's gone. Now, without doing the problem on paper, if I was to ask you what R Thevenin was, what would it be when I remove that inductor and look at the dangling leads and go ahead and measure it? What would it be? Anyone?
6 ohm?
Take a careful look.
Would be 2 ohms in parallel with 6 ohms.
I want you to take a look at this. You're saying the wrong word here. Maybe it's glare. I want you to take a look at that. There's the inductor, it's taken out. What would the resistance across that inductor be?
8 ohms.
How many see it's 8 ohms? Thumbs up if you do. Can you all see this or not? I'm looking at people. I'm not sure if you can see what I'm doing here. Y'all see that? There's 8 ohms, right? It's here. 2 plus 4 is 6 plus 2 is 8. They're all in series. There's no parallel. Y'all see that?
Yes.
The inductor is right there. Are you with me, class? This is critical. You see this. So right off the bat, I got R Thevenin. I've got the current as t goes to infinity, right? Now I'm talking my way through this so you can see it. Now I'm looking at the problem. Now I want to get the current at t less than 0. Well, what does this look like for t less than 0?
Short circuit.
Short circuit, right? Y'all hear that?
Mhm.
If it's a short circuit, we can just connect this 2 ohm in to ground if we wanted, right? Or we can just draw a short circuit, right? Do you follow? How many follow me here? We're going for t less than 0. I'm trying to just inspect this, find out what I can before I go through a lot of redraws and calculation, just talking to everybody. Try to tell you what you can see just by stopping and looking. So if that's a short circuit, isn't effectively this 2 ohm in parallel with 6 volts? Take a careful look now. If this is a short circuit and this is for t less than 0, then that 2 ohm is across 6 volts, isn't it?
Yes.
What would the current through that 2 ohm be?
3 amps.
3 amps. You'll notice one other thing. This part of the circuit had no bearing on this. Do you follow me? No bearing on the current, right? It had a bearing on the R Thevenin, but it had no bearing on the current for t less than 0. One thing that I see in this class is that people try to find a way to incorporate every element into the solution. That is a wrong method of thinking. Do not think that way. Don't try to think about partial credit points. Oh, he must use this. No, that's where you're really going to get yourself hurt, especially with some of the stuff coming up. You think about the process laid out and logically deduce things, and don't worry about components that have no bearing. There are going to be plenty of them in the future. So here we've determined the current for t less than 0 is 3 amps. We've determined the current as t goes to infinity is 0. We've determined R Thevenin is equal to 8 ohms, right? What is tau? L over R, correct, class?
Mhm.
L is 2 over 8 would be 1/4. Do you agree?
Yes.
Now we have everything to write an equation for the current t greater than 0 without ever redrawing that circuit. Do you agree with me? Now I'm going to redraw it for t greater than 0, but I want to make sure you see how I went through this without ever redrawing it. Are you with me? I'm doing it for a reason. Because if you can stop yourself from just writing ferociously and look at a problem for a bit, you will find most of these problems are very, very easy to understand. But if you rush at them and don't really think about what you're doing, you're going to come down on the wrong side all the time. All right, now I'm going to do this. I'm going to go for t greater than 0. Y'all give me, we got the current for t less than 0 through that inductor. Are you good with that? All right, I'm going to go ahead and redraw that circuit for t greater than 0. Hmm, 2 ohms. I know that I of t is equal to k1 e to the minus t over tau plus k2. I'm just rewriting a general equation. Now, we found from the discussion that K2 was the current as t goes to, the current at t less than 0, which is equal to the current at t equals 0. And that was 3 amps. Agreed, class? Now, we also found that our Thevenin here was equal to 8 ohms, correct? Restating what we have. From that 8 ohms, we immediately get tau, which is equal to L over R Thevenin, and that's equal to 2 over 8. And therefore, tau here is equal to 1/4. The units of tau are seconds, by the way, if you care to know. Now, there's one thing left to be done, K1. Agreed? To get K1, I have to find that value using the value of current as t at t less than 0, which is the value at t equals 0. Something I failed to mention is that current, like the voltage in a capacitor, current through an inductor is continuous. It cannot jump. Can't go from 1 amp to 10 amps instantly. It's continuous. There's always a finite slope. Do y'all follow me on that? Now that's real important. So that means I can say generally now, here's the equation I have. I have I of t is K1 e to the minus t over tau, or 4t, right? Because 1/4, 1 over 1/4 is 4, plus 3, right? Agreed, class?
I thought we said that the current was 0 as t approached.
I'm sorry. You're right. This is my bad. K2 is 0. And I'm so glad you said that. That was not intentional, but thank you. It goes to 0. My bad on that one. K2 is 0. That's right. So if K2 is 0, how do we get K1? Now I gave it away. Yep. You were right. Was it Brooke or not?
Yes,
All right, Brooke, how do I get K1? You're absolutely right.
you just set that equal to 3 amps. And then
At t equals 0, so K1 is 3, right?
Mhm.
Okay, my bad. I of t equals 3 e to the minus 4t amps. Now that's I of t. All right. But I'm not done. What was asked for in the problem? Okay. The voltage across this resistor is what's actually asked for. Do y'all follow me? You need the current to get it. Now, there are going to be things you see on the internet and in other books and in even this book where they say you can write an equation for that voltage. Do not, I repeat, do not go that route. There are a lot and a whole bunch of pitfalls on that. Always find the current through the inductor and then get anything else you need. You hear me? Now, I'm speaking from a lot of years of experience. If you try to do that, you're going to find yourself really going to get hammered bad when it comes to certain types of problems that you can't use that method for. What I'm showing you is a method that will work all the time for any possible situation of a transient. Now, if that's the current flowing here, what is the voltage plus to minus here? Can somebody tell me how to do that besides you, Jessica, and John, and the others who've spoken? Somebody else. Anybody? Nobody. Huh?
Would you multiply it by the resistance?
Yeah, that would give you a voltage, but there's one problem with that. Can anybody tell them, open it up for anybody? What's the problem?
The current's coming in the negative node, so the voltage is going to be negative.
Right. So what we need to do is take into account not just R times I of t, but the polarity looked at. So the plus is on the top. This current is going to create a voltage this way, right? It's going to be I of t times 2 would be a plus minus voltage. Agreed? But because the plus is on top, the actual V naught of t will be minus I of t, my I of t times R, which is 2. Or it's going to be what? Minus 6e to the minus 4t, right? For t greater than 0. Greater than or equal to 0. Do you all agree with that, class? Who asked this question, by the way? Somebody, I don't know who asked it. Anybody? John?
me.
Okay,
Yeah.
thanks, Joe. That's still, see, that's one where it doesn't have a final value that's not 0. Now, this is a tougher problem. Now, I want you to look at 3.44. We're going to talk about it. Are you with me? Now, I'm going to start for t less than 0. I want everybody to take a look at this for the discussion. For t less than 0, nothing changes with time, right? You agree?
Yes.
That means this is a short circuit. Do you all follow me on that?
Mm.
Now, if that's a short circuit, you see these two are in parallel, aren't they? Are you with me? If that's a short circuit, these two, the 4 and the 6, are in parallel, aren't they? Right?
Yes.
It's for t less than 0. Well, that's interesting and important. Now, if you have 6 in parallel with 4, I'll tell you what, just leave it 6 and 4 right there for now. We care about the current through the 6 ohm, right? That's what we care about, IFT, but we don't really want that. What we want is the current through the inductor, don't we? That's always what we look for. So this problem requires you to define a direction for current. I'm going to intentionally put the current in this direction. You don't have to put it in that direction. Follow me? I'm just doing it that way. Now, having said that, I want you to look at this. This is the kind of problem that I'll get all sorts of complaints about. And some of these are justified because it requires several things to think about. It's not just 1 or 2 little things. All right, if I want that current and I look and I got 4 ohms, this switch is closed and 12 volts, and I got 3 ohms and 6 volts. I look at that and I'll tell you right now, you could put a voltage here and you could do nodal. You could use mesh analysis, but the way I would do this, and this should start clicking with you, I would do source transforms, and here's why. Now listen carefully. When this is a short circuit, I know I have 4 and 6 in parallel, right? Really what I want is this current though, right? Isn't that right? I want the current through that 2 henries. So if I do a source transform, I take 12 by 4, I get 3 amps, right? Now listen, I would have 3 amps, right? And it would be in parallel with 4 ohms, wouldn't it? Now, I'm not going to draw it right now. I'm just talking my way. Do you agree with that at least? I would have 4 into 12 is 3 amps in parallel with 4. Okay, and I can see that 4 and this 4 I could absorb into 1. That's fine. Just leave it alone at that. Over here, I've got 3 and 6, so I could get 2 amps in parallel with 3, right? Are you with me on that? I'm going to redraw that. Okay? I'm just going to redraw that part. This is for t less than 0. This is a problem that makes you think. So I'm going to go ahead and do that. And first I have 3 amps. And it's in parallel with 4 ohms. This is going to be for t less than 0. Then I have the thing I want right here. This is the current I of t that I'm looking for t less than 0. Then I have 4 ohms here that I don't care about yet. Remember, I'm after that current through the inductor. That's where it is right here. And then I have 6 ohms here. And I have 6 volts by 3 ohms is 2 amps in parallel with 3. this is 2 amps. Do you agree with me so far? Remember, I want this current right here. That's something I want. Maybe I should do this to signify. Now, are you with me so far? I'm trying to show you how I do this. Now, y'all see that these two 4 are in parallel. What would the equivalent be?
2 ohms.
Yeah, 2 ohms. I could replace that by 2 ohms, correct, class? With me? Now that 2 ohm would be in parallel with 3 amps, so I could replace that with a voltage source in series with 2 ohms. And my voltage source would be plus or minus 2 amps times, 2 ohms times 3 amps, or it would be 6 volts. And it would be in series now with 2 ohms. Now what I've effectively done is replaced all that. And here's where my wire is, where I want this current for t less than 0, where the inductor is. Now I come over here, and what is 6 in parallel with 3, class? 2 ohms, isn't it?
Yep.
Yeah.
Right? Yeah, 2 ohms in parallel with 2 amps is really what? 4 volts in series with 2 ohms, right? So now I'm going to go ahead and I'm going to put 2 ohms here, and then I'm going to put 4 volts. Y'all agree with me? I'm doing it this way because source transforms, to me, are easier to use and see. A source transform is very, very, very useful. That and Thevenin are the 2 godsends when it comes to solving circuit problems. Now, when I look at this, if I want that current, can anybody tell me how they would do it? And I'll tell you how I would do it then.
You have 6 and 4 going to the same direction. You can
Not the same direction, opposite, right?
opposite direction.
6 is trying to push this way, 4 that way. So what do? You're absolutely right about this.
You add them.
Yeah, and what she's getting at is this. If you take these 2 voltage sources, and that 4 volts can be anywhere. It can be between these points, between this point. Doesn't matter, as long as the polarity is plus to minus, trying to drive current in the counterclockwise direction. I can take 6 volts, it's trying to drive current in the clockwise direction, 4 volts counterclockwise, 6 minus 4 is going to be 2 volts. So the equivalent of that circuit is this. Plus to minus 2 volts, right? And I can add the resistances. I'm not going to justify that, but they're in series. And that's 4 ohms, right? And then I have that wire, and really I'm after the current in this direction, am I not? I simplified it a little bit. Y'all follow me? There's 4 ohms that oppose the flow of current in this circuit. Does everybody get that? And that means this current is what? 2 by 4, right, is 1/2 of an amp, right? How many see that? 2 volts by 4 ohms is 1/2 of an amp. So I, through that inductor for t less than 0, is 1/2 of an amp. That was the key thing to this problem. Now that problem is this problem right here, going through a couple of source transforms. Never source transform the thing we want, the current or voltage, either the current through or the voltage across. That's part of it. Now I go to this, I'm going to bring back the book, so to speak, and I look at this. Look with me, class. Now for t greater than 0, both of these switches flip, don't they? Don't they? They open up. What effectively happens? Aren't both of these taken out of the circuit per se? They can be ignored. Now, I want you to see this, please. You see how there's only a 2 Henry inductor there. This 4 ohm has no bearing on what happens. That 3 ohm doesn't either. Do you all see that? The only thing that's going to have a bearing are the 6 and the 4, correct? So what would R Thevenin be when this inductor is taken out? Remember, that's not there, that's not there. What would R Thevenin be, class?
10 ohms.
10 ohm. How many see it's 10 ohms? I'm really trying my best to get this across. Now, once you have that, we have tau, don't we? Agreed? I mean, how many know we got tau? If we've got R Thevenin, we better have tau, right? It's L over R. Now that we have that, back to t greater than 0. That's the circuit for t greater than 0. What is the current going to be as t goes to infinity? Brooke noted this last time when I made a mistake. Anybody?
It's going to go to 0.
It's 0, right? There's no sources, it goes to 0. It's that simple. So we've got an equation. Now listen, we got an equation for the current, don't we? Let me just pull it out here. So now I have the current. I of t is equal to k1 e to the minus t over tau. Tau was equal to L over R, right? That was 2 over 10, or 1/5, or this would be minus 5t, or t times 5. And K2 is 0, right? Now, please just listen to me. We get K1 by setting it equal to what? The I of t less than 0 is I of t equals 0 is 1/2, right? And therefore, K1 is 1/2. So that's 1/2 here, e to the minus t times 5. And that's true amps. Now, that's the current. But I want you to notice what he wants. I'm going to draw the circuit for t greater than 0 here. For t greater than 0, we have this. We've got 4 ohms. We have that inductor, and we have the current I of t through it, right above. And then we have 6 ohms here. This is the effective circuit, right? Those other 2 resistors are inconsequential because they're out of the circuit, aren't they? But what's asked for in the problem? They want this voltage. Right there. Now, what is that voltage? Well, I of t is going this way. So in a sense, you could just say, well, minus I of t is going this way, isn't it, class? So minus I of t times 4 would be that voltage, and that's it. So it'd be minus 4 times I of t, or 1/2 times e to the minus 5t would be, in fact, the voltage, which is simply minus 2 e to the minus 5t. Do you agree with me? Finally, and I hope I'm answering questions that you had in the back of your mind about this. I know it's a football weekend. That's part of the reason I'm going like this. Finally, inductor problems can take all forms. Here's one that we haven't worked. Work with me. Well, we could have worked it. It is not recording. Oh, it is recording, right? Is it recording or not? It is. Thank you. Just making sure. All right. Now, do this with me. Let's see who can work with me on this. Here's a kind of quiz problem I would ask, for real. 20 volts, all right? Resistor, 10 ohms. Switch. T equals 0, it shuts. Right?
Can you move the paper over?
Yes.
Thank you.
Welcome. All right, now, here's the deal. I want V of t. Quiz type question. Follow me? I'm after V of t. Notice the polarity. I give you a situation where there are two switches. Listen. The first switch is in a closed position for t less than 0, and it opens at t equal to 0. Follow me? It's shut, but then it opens. Now, when that opens, this goes away. Y'all with me? But I got a switch that was open and closes at t equals 0. Are you with me? That will be there for t greater than 0, and it will be the source that dominates what happens. Now, when we do this problem, here's where you have a little choice. You can choose the direction of I of t unless I specify it. If I say I of t goes this way, then V of t would just be 10 times I of t. Does everybody see that? Okay, now what I'm going to do is this. I'm going to look at this and do it in stages. For t less than 0, right? That switch is open, right? You can ignore it. Do you agree with me? I mean, this switch is open, ignore it. That switch is closed, a short circuit, right? How much current circulates around here? It'll be going this direction, but what's the value of the actual current circulating counterclockwise? What do we replace this inductor with, class, for t less than 0? Short circuit, right? If it's a short circuit, y'all see we got 10 divided by 10 is 1 amp, right? But it's going counterclockwise. I want the current in this direction. So that means I, through the inductor, I'll put it IL of t, for t less than 0 is minus 1 amp. Do you follow me? I'm about out of time. If you need to go, so be it. It's at 1:50 my time right now. Are you with me? I'm going to finish this though. Agreed, class? Now, when the switch does its thing, both go concurrently, this opens up, that's gone, right? This middle one's gone, and this comes into play, right? So for t greater than 0, I got what I want for t less than 0. For t greater than 0 or equal to 0, now I've got this. There's a switch, it's closed. My inductor is right here. Got 10 ohms here. And this is I of t and IL of t in this direction. Now, look at this for a second. What is IL of t as t goes to infinity just by inspection? Can you do that with me?
It's 1 amp.
Well, what we would do is short this. You're right. You're right. That would be shorted, and we'd have 20 divided by 10 plus 10, or 20, or we get 1 amp. So that's the t as t goes to infinity. Do you all agree with that? I promise you, if I give this problem to this class cold without going through this, I would see a lot of bizarre answers. This type of problem. Next, I need R Thevenin. Work with me. What is R Thevenin for this circuit, class? What do we do with any sources for Thevenin equivalent resistance? Batteries become short circuits, right? Current source is open. There's one battery, it becomes a short, right? So what is R Thevenin, class? Just put that like that. What is it?
20 ohms?
It's 20 ohms. They're in series. Do you agree with me? All right. We can get tau. What's tau?
L over R.
Or 2 over 20 or 1 over 10. Agreed? Now we have an equation. We have I of t is equal to K1 e to the minus 10t, right? Plus the current as t goes to infinity plus 1, right? How do we get K1?
Let's substitute -1.
We solve at t equals 0 what the current is, right? And at t equals 0, the e to the minus 10t is 1. E to the minus 10 times 0 is e to the 0 is 1. And we get an equation K1 plus 1 is equal to the current, right? Which is 1.
Wait
a second.
I mean,
No, it's minus 1, pardon me, right? Minus 1, isn't it, class? Sorry.
Yes.
Brooke, if you're still there, did I mess this up too?
No, that's right. It's
I
-1.
thank you very much. So what is K1?
-2.
Thank you, -2. I'm trying to get this right, but so it's -2 e to the minus 10t plus 1 is the value of I of t for t greater than 0. Agreed, class? We're not quite done.
Can you explain again why it's a -1 for t less than 0?
Yep. Back for t less than 0. This was the original circuit, right? For t less than 0, we can ignore that part, right? Wasn't the current being driven by this 10-volt source in this direction? Counterclockwise.
Okay, yes, I see.
And therefore, the current here would be limited. 10 over 10 is 1 amp, but would be in the minus direction, wouldn't it?
Okay.
And that means the current does change directions or polarity, however you want to talk about it. You agree with me?
Yes, thank you.
Sure. All right. And by the way, it doesn't do it instantaneously. If you graph this, right? For t less than 0, it would be -2. Remember, it's -2. And then at t equals 0, -1, pardon me, -1. At t equals 0, it's -1. But then it would what? This part would decay and it would approach 1 as t goes to infinity. Do you all see it? So it goes from -1 to 1 exponentially. Agreed, class? Now, that wasn't what was asked for, though. This is a circuit for t greater than 0, but I wanted this voltage. Now, please pay attention. What is that voltage V of t, class? Remember, that current, what is it? And now it's simple, the way I've drawn it. What is this voltage, class?
10 times that current.
It would be 10 ohms times I of t, right? We have I of t, correct? So 10 times that. Y'all see this? Just give me some indication you get the lecture material today. All right, now I'm trying to be absolutely crystal clear about this. And I'm going to tell you what we're doing on Wednesday. We're going through, yes, go ahead. Unmute yourself if you had a question. Oh, you didn't have a question, sorry. What we're going to do on Wednesday is power. Now, power requires, I know this is officially my office hour. Please don't send me hate mail that you're going over. You don't have to be here. I'm just telling you a little something that may help the rest of the class. On Wednesday, we're doing power. Power is really voltage times current, but it will require you to understand something called RMS voltages or RMS calculations. That's root mean square. How many have used RMS calculations in the past? Anybody? Mechanical engineers should have done this for all your RMS surface area. I'm sure aerospace engineers have used this. I'm assuming, of course, that you've had your classes, the higher level classes. If you haven't, then you don't know what I'm talking about. It's actually very simple. And I'm probably not going to, no, I'm not going to do it right now, because if I do it, I know what happens. You know, you try to be nice no matter what happens. No matter what I do, I'm going to be criticized. So what I'm going to do is postpone that for next time. But now, this is an office hour. Do you have questions about any of the lecture material from the past?
Dr. McGinsky, could you go over the source transforms again?
Source transforms? Okay. All right. Are you all with me? This is an office hour. How many people are left, by the way? I cannot tell.
20-ish.
How many?
23, 22.
23, 22. Okay, that's all right. That's all right. So if this is an office hour, here we're going to do it. He asks for source transforms. And what it says is this. If you have a resistor R in series with a voltage V, these are two terminals, A prime. Guys, whoever's making a racket. All right, whoever, all right. This is equivalent, exactly equivalent to a current source where I here is equal to V over R in parallel with that resistance. And these, between these terminals A and A prime, anything can be on that side, but these two circuits are identical for their output between A and A prime. Who asked that question, by the way? Okay, I hope I
That was me.
answered.
Thank you.
Sure, you're welcome. And by the way, if somebody can answer chat questions, if you want to interact, please do. I don't need to be on chat. I need you to interact with yourselves. Believe it or not, you two, your classmates can help you more than I can. And I'm guaranteeing you in about every class I've ever been in, that I've been a student or a professor, that's true. The actual classmates can do more good for you than usually the professor or the lecturer. Now, questions about the content from the last lectures, anything at all? Anything at all?
This isn't about. Oh, sorry. Go
Sorry,
ahead.
you go. You go, John.
Okay. Well, did you get my emails about missing the quiz Friday for my interview?
Probably. Well,
Okay, well,
all right, that's another thing. Are you still there, Jessica, or no?
Yes. I'm
Okay,
sorry.
Jessica, remind me next. You seem to be there. You record, and I appreciate your input all the time. And Brooke too, and Gabby. I appreciate everybody that gives me input. John, and I forgot who else, but a lot of people. I'm going to have one makeup quiz after everybody is done with their COVID-19 and all other men. And what it's going to be is this. Now, the reason I'm doing this is because this class has got people that have missed 2 or 3 quizzes and they still have COVID and they're coming back. It's going to be one makeup that covers the same material. It's not just the material in the quiz you missed. Got me? It's going to be all the material up to the point. In other words, the material you're being taught now, you'll be quizzed on. And it will be done after everybody is healthy towards the end of the semester. Now, that may seem terribly unfair. There's no way to handle this. I've got literally 50 or 60 makeup quizzes right now that I have to somehow organize when people get healthy. And it's almost impossible because they're healthy one day, then I got a failed check. I even schedule quizzes and they say I failed my health check. So this kind of stuff is going to stop in a heartbeat. We're going to have one quiz that covers, it's going to be for everything. And then I will replace your missed quiz or quizzes with that grade. Okay. And it's going to be fair. It's going to be on the material. It's not going to be some bizarre thing out of the pit. It's going to be a fair quiz that's not going to stretch you to a point of breaking. But it does require you to understand what's going on because all the material builds on the past with the exception of the AC circuits. You need all the tools in your box to do them. That's the reason. Now, other questions?
Is this quiz going to be like typical quiz links, 1 2 questions?
As all the other quizzes, it's going to be a couple of questions about a circuit. I'm not, you know, you get the idea. You've had my quizzes. You know what's going on. Other questions about the material?
I got one question about the quiz.
Okay, go ahead.
So for the previous Friday quiz, where can we pick it up somehow? And
Yeah, contact, send, you got Chun-Li's email, don't you? The grader?
You mean our TA?
Yeah. Just
he sent to us, I think 3 weeks ago, but never sent to us again. So
no, just send him an email. He has the quizzes. If you want, just tell him you're coming. He'll give it to you. He's got them in his office.
All right.
And can you remind me of that too, or whoever's left? Jessica, you're still there. Good. Remind me of that one too.
Okay.
All right. All right. What other questions about the material?
I have a question
Go
from
ahead.
today's lecture on the problem where you did the source transform and you got one voltage source over here and one over here.
Yeah.
Why can you just add those two together? And is there any case where you cannot just
All right.
add?
Let me ask you this. If you had this, just go with me here and I'll build my case. If you had a voltage source here, and I'm just going to label it 10 volts. And you had a voltage source here, and I want to label it 5 volts. Forget everything else, all right? And I wanted the voltage between here and here. Can you follow? Hold on. Okay. And you want the voltage between here. You take what? You put the negative lead here, and then you work your way to positive. You see an increase of 5, increase of 10. Put the positive lead here. That would be 15 volts, right? Now you notice no current's flowing, right? It's an open. If I put a resistor here, 10 ohms, no current's flowing, correct? How much voltage do you read here? Increase of 5, nothing. Increase of 10, you read 15 volts, right? Isn't that right? All right. What if I put another resistor here? What do you read? Voltage between here and here. I can't hear you. You're muted, Gabby.
Sorry, I'm talking to Emma trying to figure out what's going on.
Don't worry, she'll figure, both of you figure out. What these do nothing is the point. If there's no current, there can be no voltage drop. That's my point. All right. If there's no voltage drop, the current here is still 15, right? The voltage is 15 volts. Do you see that? Now listen carefully. What is the voltage here no matter how many resistors I put in series?
15, I guess.
Yeah.
Just because you said it.
Yes. No, the reason is these don't have any voltage drop. If there's no current, there can't be a voltage drop, right? All right, now keep with me now. Now, if I do this, current flows, doesn't it? How much current would flow? Well, you know there's 20 ohms limiting current, right? They're in series. Do you agree with me? They're in series. Doesn't matter where they are. That 10 ohm could be relocated here. They're all in series. The same current flows through each one of those things, right? Gabby? All right. What's forcing that current to flow? 15 volts, right? Right? That's it. Voltage is like a pressure. It doesn't matter if there's one voltage source here, another here, as long as the amount, when they're added with no current flowing, is 15 volts, the current will be limited by the 15 volts. It would be whatever.
So as long as they're in series, you can add them?
Yes.
Okie dokie.
Yes.
Thanks.
All right. Believe it or not, sometimes people are afraid, well, you know this, they're afraid to ask obvious questions because they could look silly or foolish or something. Don't be. Ask the questions that are foolish. Those are the ones that are most helpful. And the problem is because I'm in electrical and computer engineering, I don't have the best tools to make this clear to you. I don't know how to make this similar to something you saw in some industrial class or mechanical or whatever. So you got to help me sometimes. And Zoom is more of a challenge than you think. Teaching on Zoom is by far the hardest for me because I cannot read the class. I don't know what they're thinking, what they're doing. I don't know where they're uncertain or where they're confused. All right, another question. Did that answer, Gabby?
Thank you.
Jessica, did you have a question?
Yeah, it's about the last quiz. If we could go over it.
Yeah, the solutions are up, by the way, on Canvas, aren't they?
Yeah, I just wanted like a step-by-step thing of it.
Yeah, sure. Let me find the last quiz if I can. I don't even have OneNote open. Hold on. Ba-dum. Andrew, are you on? I see some kind of an icon, but. Is this it? This is it, right?
Yes.
All right. For starters, I mean, that quiz solution is out there. So for starters, y'all see how, I mean, do you see how there's no voltage across this capacitor? I'm going to go ahead and do something. I'm going to do this. I'm going to put a plus there, and I'm going to put a minus here. And then I'm going to say that's VC of T. That way, just leave it. That, I'm just trying to make sure you see the polarities. I hope they show up. This one didn't. I think you get the idea. That's plus, that's minus, okay?
Mm-hmm.
All right, so if you look at that, VC for T less than 0
Is 0.
is 0 for starters, right? Now, what is VC as T when the switch closes?
Okay.
Well, how much current can flow through that for T equal infinity? That's what we'll get. We'll get VC for T. Matter of fact, let me do it this way. Sorry. Well, all right. Now, as T goes to infinity, this becomes an open circuit, doesn't it? Jessica, the capacitor?
Yes.
So if that becomes an open circuit, no current can flow through it, right?
Yeah.
If no current can flow through it, this resistor has no bearing on that voltage, does it?
Mm-hmm.
So that means this voltage is really the voltage across the 3K, isn't it?
Mm-hmm.
As T goes to infinity, what would the voltage across the 3K be? I mean, are you with me so far? That voltage would be what? It would be 3 over 3 plus 6 or 9. It would be 3 over 9 times 12, wouldn't it?
Well, yeah. What I did, I considered the 2 also in it. I did 3 and
No,
2.
the 2K has nothing to do with no current through there, right?
Yeah, that's where I got wrong.
That's the problem. Yeah, it's just simply that voltage is simply 12, and then it's going to be 3 over 9 or 1/3, right? And that's simply 4 volts, isn't it? That's all it is, right?
Wait, we don't consider 2 because
There's no current. There's no voltage drop if there's no current as T goes to infinity, right? Look, as T goes to infinity, this is an open circuit. No current can flow through it. Isn't that right, Jessica?
yes.
If that's an open circuit, no current can flow. There's no voltage drop here, is there?
Mm-hmm.
That means what? That negative can start here. If you're going to take the voltage from the negative to the positive, no voltage drop there, then it's going to be minus the plus the voltage drop across here, which would just be this, the voltage drop happening in this circuit, right? With me?
Yes.
That's all it is. Now, what is our Thevenin though? Well, when the switch closes, what do you have to do? When the switch closes and you do the Thevenin equivalent resistance, just remove that capacitor mentally. Then you have this 2K, don't you?
Yeah.
And then you have 2K, and then there's 3K in parallel with 6, which is 2K, or you have 4K for our Thevenin, don't you? You see that?
Yes.
So then you've got what? Tau is equal to R times C, or it's 200 microfarad times 4K, right? Or 0.8 seconds, isn't that right?
Mhm.
And then you write the equation, but that's how you do that one.
And then how you find the VO? Is it just the negative of VCT?
No. For here, I'll tell you what. I'm going to work this out so you can see the steps, but let me pull that over here. All right. When we take a look, this will be for t greater than 0, right? We know that VC for t less than 0 was 0. We knew that, right?
Mm.
Now for t greater than 0, here's the circuit. That switch is closed, right? Then I got 3K here. Then I have this capacitor, right? And then I have 2K.
Mm.
And I want this voltage, right? Correct?
Yes.
Now I know this voltage, or at least I should know that voltage, right? That voltage is what? VC of t is equal to K1 e to the minus t over 0.8, right? Plus K2. And that voltage was what? We figured out K2 was 4 volts, didn't we?
Mm-hmm.
Now we get K1 as minus 4 because the voltage at t equals 0, 0. So I have VC of t is equal to 4 times 1 minus e to the minus t over 0.8, or tau, for t greater than 0.
Mm-hmm.
Okay, now that's the voltage. Now next, after that, because I got the 4 volt, I need this voltage, V out of t, right here. So what I need is, I need to go ahead, and you can do this several ways. I like source transforms, you know that, right?
Mm-hmm.
Just keep watching. If we do a source transform on this, I would get 12 by 6, or that would be 2 amps, right? Now, you don't have to do it this way. If you want to do it nodal, we can do it with nodal. You could do it a variety of ways. 2 amps that way. That's in parallel with the 6, right?
Yes.
And then there's a 3K, correct?
Mm-hmm.
Here's the VC that you know. And here's your resistance here, 2K, right? And this is where we want the voltage, right?
Yes.
Okay. Now, can you see that that's 2K?
Mm-hmm.
So 2K in parallel with 2 amps is really what?
4.
Right. 4 volts, right? Right? And then it's in series with 2K, isn't it?
Yes.
Then there would be VC here. And then there's 2K here, right?
Mm-hmm.
Now, I want this voltage, right?
Mm-hmm.
All right, take a look at this. This should be obvious. You see I have 4 volts trying to push current this way, and I have VC trying to push current this way, right?
Mm-hmm.
That means the net voltage is what? 4 minus VC of t. That's the net voltage I have, isn't there?
Yes.
And what do you want to do? You want to do voltage division. You know both of these are 2K, right? So it's just half that. That divided by 2 is V of t, V out of t.
Okay.
Now you also see when you plug in this V here, you get 4 minus 4, which goes to 0. Then you get minus a minus 4 plus 4 e to the minus t over 0.8 over 2, or it's 2 e to the minus e to the minus t over 0.8. Okay. But that's how you do it, Jessica.
Thank you.
The reason I give everybody 3 points is the last part I haven't covered with a variable voltage source after the switch closes. So okay.
Thank you.
How did you do, by the way?
Mm-hmm.
You don't have to tell me if you don't want. Because I didn't really look carefully at all that. I know.
I was very confident before it because I did so many exercises, more than just the homework ones. And I was like, okay, this is easy. There's nothing that could go wrong. But what I got wrong when he first for t less than 0, I got that right. But then when you say for t goes to infinity, I shouldn't consider the other 2 on the side. But then I did a voltage division. I did 3 and 2 in parallel. But then you said if it's open, then the 2 doesn't count. It's supposed to be just 3 and 6. But I consider that too. And that place, I got 2 volts as my t goes to infinity.
Oh, now let me tell you this. When you're doing these problems, it pays dividends. Just replace the device with the actual, the equivalent. So if it's an inductor, a short circuit, t equal infinity. If it's a capacitor, an open. And then you can't go wrong. Because an open circuit, no current can flow.
Yeah. Mm-hmm.
That's it.
Mm-hmm.
Okay. Andrew, did you have a question? I see your icon. Are you there? Well, I try. Anyway, anything else, Jessica?
No, that's all. Thank you.
Sure.
Are we having quiz this Friday?
Think so. Why? Is there something happening?
No, I'm just asking. So we're gonna cover power on Wednesday, and okay.
Yeah, we're gonna try. And unfortunately, I can't give you much until I go over some of it, but maybe I will. I'll see what I can do.
Okay. All right.
I mean, you're getting this stuff though, or not?
I am.
You're mad at yourself, I bet.
Because I don't know, I was very confident about this. I think the only material so far that I wasn't 100% confident was the one with the angles, where we had to do find like half the angles, the sine, cosine, things like that. But this one, I understand. I feel like once you understand what happens when it closes, when it opens, the calculation itself is not hard, but it's just understanding what's going on when it's open or closed, what's going on in the whole circuit.
Yeah, and always put in the equivalent, if it's an open circuit or short, and then you can't go wrong. But I'll tell you, I don't know how many times I can say this, and I guarantee you they'll mess that up. They won't do it. Some people won't. And that I'm sorry for. I hope I'm getting through, you guys. I'm really trying, but it's difficult. Oh, you know what? I got to do a poll. Hold on. You got a second?
Yes, sir.
I got to poll everybody about if you want in person or if you want remote for everything. Okay. And the only way I can get a poll out there is a Zoom poll is I got to have people out there. Hold on for 1 second. I'm not a real fan of Zoom, but I tell you one thing, it beats not being able to do a class. And all right, now there's polls in here somewhere. Where is that? I've actually done one poll with you guys, I think.
You did the exam one.
Where's the polls? Polls, they're there. Dumb question. Ask a question. I'm going to write it down. Why is it asking me to sign in? Hold on. You're there, right? It's still there. Can you see that?
I can see your screen.
All right. You see where I'm on polls?
No.
You don't? Oh, you don't see? I mean, do I still have a shared screen here? Do you see like a bunch of icons on the desktop?
I see a bunch of icons, yeah.
But you don't see poll. Okay, that's invisible to you. Okay.
You have it open?
Not yet, but I do now. Do you see it?
No, I don't see it.
All right, hold on. Not the poll, but I mean, do you see anything on here that says polls on this screen right here? Can you see my cursor?
Let me see. Yes, I can see your cursor. It's on Dropbox, yeah.
Do you see this? The poll or not? You see polls?
I see Dropbox, but no.
Never mind. It's not.
Yeah, it's still open. I can just see your screen with the icons in it.
Okay, how come this darn thing? Hold on. 8-4, stay there. F4C. Are you on campus right now?
No, I'm in my place.
I wonder how many people are on campus. I saw one person wearing a mask. All right, now, what is it asking? Join the meeting. I'm the host. This is going to be funny. I have no idea what's going to happen here, Jessica.